Hello viewers, I Ch05 welcome you to the chapter of binomial distribution. In this chapter we shall discuss on one of the most important discrete probability distributions called the binomial probability distribution. We will discuss the derivation of the various probability functions and constants of the binomial probability distribution and also fit the binomial distribution of the given data. Before proceeding to study the various types of topics of probability, we will first acquaint ourselves with the terms which are going to be used in the discussion. What we shall discuss about these topics, but we must first understand the following concepts before proceeding further. Frequency distribution, where only two mutually exclusive outcomes are possible, such as better or worse, gain or loss, head or tail, rise or fall, success or failure, yes or no. So therefore, if the probability of success in any given trial is known, binomial distribution can be employed to compute a given number of successes in a given number of trials. And it can be determined if an empirical distribution deviates significantly from the typical outcome. This distribution was first studied by J. Bernoulli, a Swiss mathematician, in about 1700, and for this reason this distribution is sometimes referred to as Bernoulli distribution as well. The binomial probability distribution studies a mathematical model in which an experiment is repeated several times, where each performance of the experiment is called a trial. This model is developed under a very specific set of assumptions, which are described as follows. The first one, the experiment consists of a series of n identical trials. Second, there are only two possible mutually exclusive outcomes in each trial, called success and failure. Third one, the probability of success remains constant from trial to trial. Fourth, the trials are independent. That is, the outcome of any trial is independent of the outcome of any other trial. As an illustration of what these four conditions mean in practice, consider the following example of a fax machine salesman who makes 10 sales calls on small and medium-sized businesses every day. Each of these 10 calls is a trial, and the conditions under which they take place are assumed to be identical. Condition, the first one, at each call the salesman either sells a fax machine, that is a success, or he does not, that is a failure. So there are only two possible outcomes at each trial. Now condition second, we further assume that the probability of him making a sale and also therefore the probability of him not making a sale at each call is the same as the probability at every other call. Condition number third, for the purpose of this example, we assume this probability of him making a sale is 0.38. The probability of not making a sale is going to be 0.62. We finally suppose that the decision of each business as to whether or not to buy a fax machine is independent of the decision of each business as to whether or not to buy a fax machine is independent of the decision of all the other businesses. Condition number 4. Thus, this experiment satisfies the four conditions of the binomial distribution, and a random variable defined as a number of successful sales calls in the total of the 10 calls will be distributed as a binomial distribution. The importance of recognizing that any particular random variable has a binomial distribution is that we can then very easily determine the expected value and the variance of the random variable, and also the probability of it taking any one of its possible outcomes. Any random experiment for which the binomial probability model is appropriate is called a Bernoulli trial. A common example of Bernoulli trial is coin flipping. For example, in repeatedly tossing a coin, say 3 times, we find that first, the number of trials is 3. Second, there are exactly 2 possible mutually exclusive outcomes in each trial, that is head or tail. We can call the occurrence of head as success and that of tail as failure. Third one, the probability of success remains constant from trial to trial. Fourth point, the outcome of any trial is independent of the outcome of any other trial. When an experiment has more than 2 outcomes in each trial, we can convert it into a Bernoulli trial by considering the occurrence of an event E, capital E, as a success and that of event E bar as a failure. For example, if a fair die is tossed 4 times, then there are 6 possible outcomes in each toss. However, if we treat getting 2 as success and not getting 2 as a failure, then we observe that there are only 2 outcomes in each trial. The probability of success remains constant from trial to trial and the trials are independent. Let us consider a Bernoulli experiment that consists of n number of trials. That is, consider an experiment that is repeated n times such that there are only 2 possible outcomes on each trial called success capital S and failure capital F. Further, the probability of success is given as small p, which is equal to the probability of capital S, remains the same from trial to trial and are independent. Since there are only 2 outcomes on each trial, the probability of failure must be then 1 minus p, and we write it as small q. So, small q represents for failure, probability of failure, which is equal to 1 minus p, which is equal to probability of capital F. Now, if x, capital X, is the number of success in n trials, then the possible values of x are 0, 1, 2, so on, n. The problem is to find probability of x when it is equal to r, the probability of obtaining exactly r successes. Now, to find it, note that in a sequence of n independent trials with 2 possible outcomes, any sequence that contains r successes and n minus r failures has probability p to the power r times q to the power n minus r. To find the probability of obtaining exactly r successes in n trials, we must find the number of sequences having r successes. The number of such sequences must be equal to the number of combinations of n objects taken r at a time, that is NCR, n combination r. Hence, the probability of getting exactly r successes in n trials is given by probability of x at r is equal to NCR, that is n combination r times p to the power r times q to the power n minus r, where r is equal to 0, 1, 2, so on n, and q is equal to 1 minus p, that is a probability of failure. Binomial distribution. Now, let us see how binomial distribution can be put. If x is the number of successes in n independent trials of a binomial experiment with the probability small p of success and small q of failure on any trial, then the distribution for x is given by probability of x at equals to r, which is equal to NCR times p to the power r times q to the power n minus r, where we know r equals to 0, 1, 2, so on n, and q is equal to 1 minus p. We usually write p probability of x is equal to r as probability of r only. Any random variable with this distribution is called a binomial random variable, and it is said to have a binomial distribution. The quantities n and p, small n and small p, occurring in binomial distribution are called the parameters of binomial distribution. Now, we will see an example. A pair of dice is thrown 6 times. if getting a total of 9 is considered a success. Now, what is the probability of getting at least 5 successes? Let's see the solution. Let small p denote the probability of getting a total of 9 in a single throw of a pair of dice. Then small p will be equal to the probability of total of 9, that is equal to the probability of getting 3 and 6, 6 and 3, 4 and 5 and 5 and 4 on through dice. So, that is equal to how many times it's coming? It's coming 4 times, so 4 by 36. 36 is the total number of outcomes when we are throwing a pair of a die. So, 4 by 36, that is equal to 1 by 9. So, that implies Q is going to be 1 minus P. So, that is equal to 1 minus 1 by 9, which is equal to 8 by 9. Now, we have the probability of success plus we have the probability of the Q, right. Let X denote the number of successes in 6 throws of a pair of dice. Then X has a binomial distribution with N equals to 6, P equals to 1 by 9 and Q equals to 8 by 9. So, that implies that the probability of X equals to R will be equal to 6 CR times 1 by 9 to the power R times 8 by 9 to the power 6 minus R, where R is again 0, 1, 2, 3 till 6. So, that let us make this equation number 1. The probability of getting at least 5 successes equals to probability of X greater than equal to 5, which is equal to probability of X equals to 5 plus probability of X equals to 6, which is equal to 6 C5 times 1 by 9 to the power 5 times 8 by 9 to the power 1 plus 6 C6 times 1 by 9 to the power 6. Now, using equation number 1, we are substituting the values here. So, that is equal to 6 times 1 by 9 to the power 5 times 8 by 9 to the power 1 plus 1 by 9 to the power 6, which is equal to 1 by 9 to the power 5 times 16 by 3 plus 1 by 9. So, 1 by 9 to the power 5 times 49 by 9, which is equal to 49 times 1 by 9 to the power 6. Let us see another example. Example number 2, a coin tossed 5 times. What is the probability of getting at least 3 heads? We will see the solution. Let P small p denote the probability of getting head in a single toss of a coin. Then P equals to 1 by 2 and Q equals to 1 minus P, which is equal to 1 minus 1 by 2, which is equal to 1 by 2. Let X denote the number of heads that occur in 5 tosses of a coin. Then X has a binomial distribution with N equals to 5, P equals to 1 by 2 and Q equals to 1 by 2. So, that implies probability of X equals to R will be equal to 5 CR times 1 by 2 to the power R times 1 by 2 to the power 5 minus R, where R is again equal to 0, 1, 2 till 5. So, that is equation number 1. Now, the probability of getting at least 3 heads means we are supposed to calculate probability of X greater than equal to 3. So, which is equal to probability of X equals to 3 plus probability of X equals to 5 plus probability of X equals to 4. So, that is equal to 5 C3 1 by 2 to the power 5 plus 5 C4 times 1 by 2 to the power 5 plus 5 C5 times 1 by 2 to the power 5. Now, using equation 1, we are having it as in a bracket we will have 5 C3 plus 5 C4 plus 5 C5, the whole thing it's multiplying with 1 by 2 to the power 5. So, that makes it 10 plus 5 plus 1 times 1 by 2 to the power 5, which is equal to 16 times 1 by 32, which is equal to 1 by 2. Let us see the next example, that is example number 3. The probability that a student entering the college will graduate is 0.4. Determine the probability that out of 5 students, first none, second 1, third point at least 1 and fourth one all will be graduate. Let us see solution one by one to these parts. The first one, first of all we have here P equals to, that is the probability of success, which is equal to probability of a student entering the college will graduate, which is given in the question as 0.4. The Q, that is the probability of failure, will be 1 minus P, which is equal to 1 minus 0.4, that is equal to 0.6. Now, let X be the number of students being graduated, that is X is the number of successes now. Then X has a binomial distribution with n equals to 5, p equals to 0.4 and q equals to 0.6. So that implies the probability of x equals to r will be equal to 5cr times 0.4 raised to the power r times 0.6 raised to the power 5 minus r. So here r is goes from 0, 1, 2, 3, 4 into 5. Let's make this equation 1. Now let's see the solution to these parts one by one. First of all, the required probability in the first case will be probability of none will be a graduate. That means we are supposed to find probability of x equals to 0. So that is equal to 0.6 to the power 5, which is giving us 0.07776. In the second case, we are supposed to calculate the probability of 1 will be graduate. So that means we are supposed to calculate p where x equals to 1. So that is equal to 5c1 times 0.4 to the power 1 times 0.6 to the power 4, which is equal to 5 times 0.4 times 0.6 to the power 4. So after calculation, we get it as 0.2592. Now let's see the third one. Here we are supposed to calculate the probability that none will be graduate. Required probability can be calculated as 1 minus probability of none will be a graduate. So we want all of them will be graduate. So that is equal to 1 minus 0.07776, which is giving us 0.92224. The last one, we are supposed to calculate the probability of all are graduate. So that means we are supposed to calculate probability of x equals to 5. So that is equal to 0.5 to the power 5, which is equal to 0.01024. So that brings us to the next example. A man takes a step forward with a probability 0.4 and a backward with a probability of 0.6. Now find the probability that at the end of 11 steps, he is just one step away from the starting point. Let's see how we'll solve this. Let p, small p, denote the probability that the man takes a step forward. Then p is equal to 0.4. So that implies q is equal to 1 minus p, which is equal to 1 minus 0.4, that is equal to 0.6. Now let x be the random variable denoting the number of steps in the forward direction. Then x has a binomial distribution with n equals to 11, p equals to 0.4 and q equals to 0.6. So that implies probability of x equals to r is equal to 11 cr times 0.4 to the power r times 0.6 to the power 11 minus r. Now here again r will go from 0, 1, 2, so on till 11. If at the end of 11 steps the man is just one step away from the starting point, then he is either one step forward or one step backward from the initial point. If he is one step forward, then he must have taken 6 steps forward and 5 steps backward. On the other hand, if he is one step backward, then he must have taken 5 steps forward and 6 steps backward. This either x equals to 6 or x equals to 5. So required probability that we need to calculate is probability of x equals to 5 plus probability of x equals to 6. So this is nothing but 11c5 times 0.4 raised to the power 5 times 0.6 to the power 6 plus 11c6 times 0.4 to the power 6 times 0.6 to the power 5, which is equal to 11c5 times 0.4 to the power 5 times 0.6 to the power 5 times 0.6 plus 0.4, that is in the bracket. Now we will have this as 11c5 times 0.24 to the power 5. Example number 5. A salesman makes a sale on an average to 40% of customers he contacts. If 4 customers are contacted today, what is the probability that he makes sales to exactly 2? What assumption is required for your answer? We'll solve this as let x be a random variable denoting the number of sales the salesman makes in a day. Then x follows a binomial distribution with n equals to 4, p equals to 0.4 and q equals to 0.6. That implies probability of x equals to r equals to 4cr times 0.4 to the power r times 0.6 to the power 4 minus r, where r is 0, 1, 2, 3, 4. Let's make this equation 1. The probability that the salesman makes sales to exactly 2 customers will be given as probability of x equals to 2, which is equal to 4c2 times 0.4 to the power 2 times 0.6 to the power 2. That is equal to 6 times 0.16 times 0.36. That is giving us 0.3456. Now, assumptions. What we have taken the assumptions here are: the first one, when the salesman contacts a customer, either it results in sales or no sales. Second assumption, the probability of making the sales remains constant from customer to customer. Third assumption, the customers are independent. So, that is the solution to this problem. In this section, we shall derive various constants of binomial distribution. Let x be the binomial variate with parameters n and p. We know n is the number of trials and p is the probability of success. Then probability of r is equal to probability of x equals to r, which is equal to NCR times p to the power r times q to the power n minus r, where r is 0, 1, 2 and so on to n. Now, we will see how we obtain the mean of binomial distribution. The mean or expected value of x, it is denoted by mu or ex, expected value of x, and is given by mu equals to summation of r p times p probability of r. So, summation of r times probability of r from r equals to 0 to n. This is equal to summation of NCR times p to the power r times q to the power n minus r from r equals to 0 to n. So, that is equal to NC1 times p times q to the power n minus 1 plus NC2 times p to the power 2 q to the power n minus 2 plus so on n times NCn times p to the power n. So, we can see it follows with the steps as shown in the graphics, and finally, we get np times q plus p to the power n minus 1, that is equal to np. Thus, the mean of the binomial distribution is np. Now, we will see how to obtain the variance of binomial distribution. The variance of x is denoted by sigma square, and it is given by sigma square equals to expected value of x square minus expected value to the whole, the whole is to the power 2. Now, this is equal to summation of r to the power 2 times probability of r minus mu to the power 2 from r equals to 0 to n. The summation, this is equal to summation of r to the power 2 times NCR times p to the power r times q to the power n minus r minus mu to the power 2 from r equals to 0 to n. So, we can see it follows with the steps as shown in the graphics again. So, we get two equations now, 1 and 2. Now, substituting in equation 1 expression obtained in equation 2, we get sigma square equals to np plus n times n minus 1 p to the power 2 minus n to the power 2 times p to the power 2. So, that is equal to np minus np to the power 2, which is equal to np out of the bracket, and in the bracket we have 1 minus p. So, that is equal to npq. Thus, the variance of binomial distribution is npq, n times p times q. Now, we will see how to calculate moments of the binomial distribution. Since the second moment of a distribution above the mean is always equal to the variance, we have for a binomial distribution mu 2 equals to variance, which is equal to npq. In similar fashion, we can show that for a binomial distribution, mu 3 will be npq times q minus p, and mu 4 is equal to 3n to the power 2 times p to the power 2 times q to the power 2 plus npq times 1 minus 6pq. The moment coefficient of skewness is given by beta 1, which is equal to mu 3 to the power 2 divided by mu 2 to the power 3, which is equal to n to the power 2 times p to the power 2 times q to the power 2 times q minus p to the power 2. The whole thing is divided by n to the power 3 times p to the power 3 times q to the power 3, which is equal to q minus p to the power 2. The whole thing is divided by npq. And the moments coefficient of kurtosis is given by beta 2. So, beta 2 is equal to mu 4 by mu 2 to the power 2, which is equal to 3n to the power 2 times p to the power 2 times q to the power 2 plus npq times 1 minus 6pq divided by n to the power 2 times p to the power 2 times q to the power 2, which is equal to 3 plus 1 minus 6pq divided by npq. The various constants of the binomial distribution can be summarized in the table shown. So, this table shows us the constants of the binomial distribution. Let's come to example number 6. In a binomial distribution, the mean and the variance are 12 and 4 respectively. Find the parameters n and p. Let's see how we solve this. We are given mean equals to 12, that is np is given, which is equal to 12. Let's make this equation 1, and variance is given as 4, that is npq is given as 4, which is equation number 2. Now, dividing equation 2 by equation 1, we obtain q equals to 4 by 12, which is equal to 1 by 3. So, that implies p equals to 1 minus q, which is equal to 1 minus 1 by 3, which is equal to 2 by 3. Substituting the values of p in equation 1, we get n times 2 by 3, which is equal to 12. So, that implies n is equal to 18. Thus, n is equal to 18 and p is equal to 2 by 3. Now, let us see example number 7. If the mean and the variance of a binomial distribution are respectively 9 and 6, find the distribution. Let us solve this. Let n and p be the parameters of the given binomial distribution. Then np is equal to 9 and npq is equal to 6. That is already given in the question. Dividing both of these, npq by np will give us 6 by 9. So, that is equal to 2 by 3. That implies that q is equal to 2 by 3 and we get p equals to 1 by 3. Thus, the equation np is equal to 9. So, it gives us n times 1 by 3 equals to 9. So, that makes us n equals to 27. Now, if x is the required binomial variable, then x has the following probability distribution. So, we can have this distribution as probability of x equals to r equals to 27 CR times 1 by 3 to the power r times 2 by 3 to the power 27 minus r, where r is ranging from 0, 1, 2 till 27. Suppose a random experiment consisting of n trials and satisfying the conditions of binomial distribution is repeated n times, capital N times. Then the frequency of x successes is given by the formula frequency of x equals to np, where n times probability of x equals to x, which is equal to n times probability of x, which is equal to n times ncx times p to the power x times q to the power n minus x, where x is ranging again from 0 to 1 to n. Now, substituting x equals to 0, 1, 2 till n, we get the expected or the theoretical frequencies of the binomial distribution. So, we will have these frequencies like n times q to the power n to the power n times c1 times p times q to the power n minus 1, and n times nc2 times p to the power 2 times q to the power n minus 2, and so on till we will have it as n times p to the power n. Let us make this equation 1. These expected frequencies can easily be obtained if p, the probability of success, is known. However, if p is not known, then first we find the mean of the given frequency distribution by using the formula x bar equals to sigma fx by sigma f and equate it to np, the mean of the binomial distribution. That is, np equals to x bar. This implies p equals to x bar by n, and hence q equals to 1 minus p. With these values of p and q, the expected or theoretical binomial frequencies can then be obtained using equation number 1. So finally, we have learned today the chapter of binomial probability distribution. In this chapter, we have discussed its meaning and the basic assumptions underlying the binomial probability model. We have also learned how to derive the different probability functions of the binomial distribution and constants of binomial distributions. So that brings us to the end of today's episode. We are ending here the chapter of binomial probability distribution, and we'll see you again discussing about our next topic on normal distribution. Thanks for watching. Have a nice time. Bye.
Thank you.